Hey everyone, and welcome. Today we are going to dive into a really powerful mathematical recipe called separation of variables. Seriously, think of it as the master key that unlocks some of the most important equations you'll find in science and engineering. So let's get right into it.
So how do we describe these things mathematically? At the core of all these real-world phenomena are what we call partial differential equations, or PDEs. And yeah, they can look pretty complex on paper, but they're really just the language we use to describe the world. So the big question is, how do we actually solve them?
All right, here's our game plan. First, we'll talk about why PDEs can be tricky. Then, I'll introduce you to our problem-solving recipe. We'll walk through a clear 5-step method, figure out the importance of ingredients called boundary conditions, and finally, see how this all works on 3 of the most famous equations out there.
Okay, let's be real. Seeing a PDE for the first time can be a little intimidating. You've got multiple variables, you've got the rates of change, and it all seems kind of tangled together. But the beauty of the method we're talking about today is that it gives us a really elegant, systematic way to untangle that knot. So let's try to think about this in a new way. Separation of variables isn't just some dry algorithm you memorize. It's much more like a master recipe from a cookbook. You know, it takes a really complicated dish, or in our case, a problem, and breaks it down into simple, easy-to-follow steps. If you follow the recipe, you get the right result every time.
So, what are the instructions in this recipe? Well, it all boils down to a super clear 5-step method. Let's walk through it together.
Okay, this is the heart of it all. Step 1, separate. We make this brilliant assumption that our complicated solution, u, is actually just a product of 2 simpler functions, one that only depends on space, x, and one that only depends on time, t. This breaks one hard problem into 2 much easier ones. Step 2, solve the boundary value problem, or BVP. Here we focus just on the space part. We apply our physical constraints and find these special numbers called eigenvalues. Think of them as the natural fundamental shapes or modes the system is allowed to have. Step 3. Now we solve the ordinary differential equation, the ODE. We take those eigenvalues we just found and use them to solve the time part of the problem. Step 4. Superposition. This is a cool principle that says if we have multiple solutions, we can just add them all up to create a more general solution. So we sum up all those individual product solutions. And finally, Step 5. Use a Fourier series. This is the magic touch at the end. We use the initial state of our system to figure out the exact amount of each of our basic solutions we need, perfectly tailoring our general solution to the specific problem we started with. You know, every recipe needs ingredients, right? For PDEs, our ingredients are the boundary conditions. They're what define the physical reality of the problem. You know, what's happening at the ends of a guitar string or at the edges of a heated metal plate.
And this is where it gets really interesting. Take a look. A Dirichlet condition, where the value is fixed at 0 on the ends. What is that in the real world? It's like a guitar string that's pinned down and can't move. And look what the math tells us. That physical setup forces us to use sine functions as our building blocks. Now, contrast that with the Neumann condition. Here, the rate of change is 0 at the ends. That's like a perfectly insulated rod where no heat can escape. In that situation, it gives us cosine functions. The physical ingredients you choose directly determine the mathematical functions you get to cook with.
Let's just pause on that for a second, because this is so important. The crucial point is this. The physics of your problem, which you describe using boundary conditions, literally dictates the mathematical functions, the fundamental shapes you have to use to build your answer. It's a really beautiful, direct connection between the physical world and the math. Okay, so we've got our recipe, and we know how to choose our ingredients. Now let's check out the 3 classic dishes that we can make using this one method. First up, we have the heat equation. This guy describes diffusion, basically any process where things spread out and get smoother over time. So just imagine heat flowing through a metal bar. The key thing to remember here is that its solutions decay over time. Everything eventually settles down into a nice, steady final state. Next, we've got the wave equation. Now this is totally different. It describes propagation. So instead of just spreading out and fading away, its solutions travel. In a perfect system, they just keep on oscillating forever. This is the math that's behind a vibrating guitar string or sound wave. It's a huge contrast to the decay we just saw with the heat equation. And finally, we have the Laplace equation. This one's pretty unique because if you look closely, there's no time in it at all. It describes a system that's already reached its final form. It's in equilibrium or a steady state. You can think of it as the after picture, like the final temperature distribution across a plate once everything has completely settled.
So there you have it. You've got diffusion, you've got propagation, and you've got steady state equilibrium. These are three completely different physical behaviors, and we can unlock all of them using the exact same 5-step recipe. I mean, that's the power and just the pure elegance of this method.
We've walked through the whole thing: the method, the ingredients, the final results. You have the recipe now. So the only question left to ask is, what real-world problems are you going to go out and solve with it? Thanks for joining me.